In this video, I'm going to talk to you about Ohm's law, which is kind of the law that governs how electricity flows in a circuit. And to talk about this law, we're going to use something called the water flow analogy, which has kind of been used for a while to show kind of how electricity works, because it's not this visible force that we can really see. So this kind of helps us make sense of what's going on here. And so we're going to talk about three key pieces here that are involved in any electrical circuit. All right, so they are voltage, current, and resistance. And so those are the three key pieces here, and you might be familiar with some of those terms here, but we're going to go through and kind of analyze them one by one and talk about their correspondence here in this water flow analogy. So I'm going to start here with voltage. And so voltage is abbreviated V in a lot of these equations here, and it is essentially the difference in electric potential between 2 points. And so in a circuit, voltage is typically provided by some battery or some sort of power supply. And so it takes 0 volts, and in this circuit it ejects like 12 volts. Oftentimes you're using something like a AA or AAA battery, which each has about like 1.5 volts. And so that is giving you a voltage, and its units are volts. And so that is analogous over here to a pump, which creates pressure in our water system here. So it takes a low pressure here at 0 pounds per square inch and ejects a high pressure up here at 50 pounds per square inch. Just like the battery takes, our circuit here, which has 0 volts down here, and ejects out 12 volts up here. And so voltage is very important in this circuit because it's this difference in potential that allows electricity to flow. If there was no difference in potential, the electricity wouldn't flow through the circuit. Because remember, kind of all energy in the universe wants to get to this low energy state, so things are going to flow kind of from high energy to low energy. So here we're going to use the current convention where we talk about current, which is kind of the flow of electricity flowing from a high voltage down to a low voltage. So you can see current here is abbreviated I. We're going to talk about it in more detail in a second, but it is flowing in this direction from the high voltage down to the low voltage. The other thing that you'll notice here is that we do have a complete circuit. That's important, again, for our electricity to flow like we talked about in the last video. So here in our water analogy system, we have this pipe system that is this complete circuit to allow water to continue to flow through the pipes here. So it is flowing from high pressure all the way down to low pressure here. So yeah, current is abbreviated I. I think it comes from the French term intensity, and that's to kind of prevent confusion with charge, which can sometimes be abbreviated C as well. But yeah, it might take a little getting used to, but electric current, is abbreviated as I. But what's important about it is the rate of flow of electric charge. It is actually the, electrons flowing throughout the circuit, that net charge flowing throughout the circuit, going again from the high voltage down to the low voltage here. So this battery is ejecting out a high voltage, and that makes the current flow through the rest of this circuit down to this low energy state where it goes back into the battery, and then there's some chemical process here that keeps the high voltage going. So that is current here, and it is exactly analogous to the flow rate over in our water system. So when we have a high pressure, water is going to flow down to low pressure, and we have some flow rate of the water here. And so that's going to kind of bring us to our third point here, which is resistance. And so the rate of the flow is determined by the resistance here inside of the pipes. And the rate of flow of our electric charge here, or our current, is determined by the resistance in the circuit. So current is basically the amount of charge that flows across a single point in our circuit in a second, and the flow rate is the volume of water that flows across a particular point in a second. And so electric current is measured in amperes or amps, and that's abbreviated as A. So we're going to kind of go to our last part here and bring it all together. And so the last part here is resistance. It is the measure of an object's opposition to the flow of electric current. So there is always some resistance in a circuit, and resistance can take the form of many different things. It's typically just things that we are putting into a circuit to power or make do something, right? So that could be something like a light or a motor or anything like that. there is some resistance there to the flow of electricity because it is consuming some power. And we'll talk about that a little bit more here in a second. But yeah, we have, again, our battery ejecting a high voltage. Current wants to flow from that high voltage down to that low voltage. But here we have some resistance as drawn here with these little squiggly lines, which is how we represent a resistor. And a resistor is a component that, provides a constant resistance, but oftentimes there's a lot of other things here in the circuit. This is just kind of, used to represent a shorthand for something that, supplies resistance here in the circuit. And so the flow of the current is directly corresponding to, or is actually inversely proportional to our resistance here, right? So typically we have a fixed voltage coming from some fixed voltage source. Like we'll be using 9-volt batteries, which will provide a constant 9 volts. And so what is going to change in our circuit is the current based on the resistance or based on what we introduce into our circuit and what its, inherent resistance is. So as the resistance goes up, our current will go down and vice versa. So over here, that's exactly analogous to like us constricting the pipes. So if we constrict the pipes, not as much water can flow over a particular point, right? So even though it's super wide here, it's very narrow, and this is, where that term bottleneck comes from. It's literally going to be our bottleneck that is slowing the flow rate throughout the entire pipe system here. And so, resistance does that exact same thing in an electrical circuit. It is resisting the flow of electricity or the flow of current and reducing our current in that system. And so to kind of close it out, we have this equation here where we say I, or the current, is equal to the change in voltage in our circuit. So we're going from 0 to 12 volts divided by whatever we have in resistance here. So our current is always going to be a function of our voltage over our resistance. And like I said, our voltage is typically going to be constant from some battery or power supply. And our resistance is going to change based on what's introduced in the system. And from there, we can calculate what our current is going to be. So this is kind of the equations again in several different forms. Typically what we'll do is we'll talk about it in terms of I equals V over R, or current equals voltage over resistance. But if you have any two of these, you can solve for the other ones. And this triangle gives a nice visual representation here where you can say, okay, I equals V over R because the V is above the R. And here you can say V equals I times R because they're at the same level here in this triangle. But that's what Ohm's law is. It's this equation that governs all electrical circuits with those three kind of components here: the voltage, the current, and the resistance. And it's important to kind of understand all of them and the relationship between them so that you can construct good circuits and eventually, power things through the Arduino. So let's kind of take a look at a couple simulations here that can be helpful. So the first right here is we have, V equals I times R, which is just another form of Ohm's law. So here, if I change the resistance, if I make it go up by dragging this slider up, we'll see that it's going to make the current go down, right? Because there's more resistance in the circuit, meaning that less current can flow. But then if I reduce it, we see that the I starts to grow and these arrows grow and the current level goes up here as well. And we can also see here if we had a way to change the voltage in our circuit, say we added like another battery and we increase the voltage, we see that voltage and current are directly proportional. So as one goes up, the other goes up. Whereas current and resistance are inversely proportional. So as one goes up, the other goes down. And then finally here, this is kind of a different look at a circuit, right? Where we have 5 volts here, and then this is a little symbol here that represents ground, or basically 0 volts. And we can imagine that these are kind of connected, off screen by some battery that's ejecting out 5 volts and then taking this into its negative terminal of the battery. And so what we see here is that we have a lot more current kind of represented by how fast these dots are moving, flowing through this branch than this branch here. Because over here we have 100 ohms, and over here we have 1K or 1,000 ohms. And so we're going to have more current flowing through the branch that has less resistance and less current flowing through the branch that has more resistance. So over here we have 50 milliamps, over here we have 5 milliamps. And then there's this little visual here, right? So the volts are pushing the amps through, but it's restricted here by the ohms or the resistance. So to bring it all kind of home, we have power. So power is, some measure of work over time. It's the rate of doing work. And so we can compute electrical power using these three things that we just learned that govern Ohm's law. So this kind of shows all of the different ways that we can compute any one of these four different things, our voltage, our current, our resistance, and our power, using any two of the other ones. But what's important here is that basically our power is going to be equal to voltage times current, or more commonly what we'll use is it's current squared times the resistance. So as we pour more current into some device, it's consuming more power, and as its resistance goes up, it's also going to consume more power. And so that's just kind of important to realize, because anything in a circuit is going to consume some power because we are ejecting power from the battery, because the battery is putting something out at some voltage and some current that is based on the resistance in the circuit. And then things in the circuit are consuming that power, because power out has to equal power in our circuit. And so that kind of brings us here to the law of conservation of energy, right? So energy is kind of power over time. And so we can't create or destroy energy, so all the energy in the circuit has to go somewhere, right? We're saying we're going from a high energy state to a low energy state. So where is that, energy going? So oftentimes it's, in the form of thermal energy, right? I talked about in the last video, the coil of wire heating up, your laptop gets hot as it's charging. But some of that in your laptop, the electrical energy, is going to chemical energy that's charging up the battery inside of there to eventually then dispense electrical energy to when your laptop is unplugged. So we can go from electrical energy to any one of these different forms of energy and back again, right? So we can go from electrical energy to sonic energy with speakers, right? We're using electricity to power a speaker, and then that is creating sounds due to the vibrations inside of it. And we can go the other way. We can, have a microphone that takes sonic energy and turns it into electrical energy. In the last video, I kind of showed how we go from electrical energy to mechanical energy, and mechanical energy back to electrical energy. We can, go from light energy back and forth to electrical energy in the form of turning on an LED with electricity, or using a solar panel to then create electrical energy. So, our electrical energy is not just, disappearing into thin air, it's going into something, and this is kind of showing some of the possibilities of where that energy can go.